Hello, today we're going to talk about structure 3.1.7. This is an HL only topic, and it's all about the discontinuities that occur in the periodic trend of first ionization energy. So let's review what ionization energy is. Ionization energy is the energy required to remove an electron from an atom in their gaseous state. And you can have a first ionization energy, which is removing the outermost electron, and then the second, third, fourth, etc., until you remove all of the electrons. And the first ionization energy is always going to be the lowest energy of the set, and then it will steadily increase. You can use the ionization energies to get an idea about the not only the energy levels that an atom has, but also the sublevels. So let's take a look at, let's use sodium for example. Sodium's electron configuration is 1s2, 2s2, 2p6, 3s1, 11 electrons. And I'm going to go ahead and draw the orbital diagram as well. So 1s has 2 electrons, 2s has 2 electrons, 2p has 6 electrons, and the 3s has just 1 electron. Okay. So if we break down by energy level, sodium has 3 energy levels for its neutral atom. When gaseous sodium loses its first electron, it's going to lose that 3s electron. All right, so I want you to imagine, I'll use a different color. This electron's going away, and that takes a certain amount of energy. So let's see if I can plot that. The first electron is going to have the lowest ionization energy of the set. Then the second ionization energy has to remove an electron from the second energy level, which is much closer to the nucleus than the third energy level. So you're going to see a big jump to the second energy level. Third, fourth, fifth, sixth, seventh, and then you will see a bit of a jump. It winds up being pretty significantly easier to remove an electron from the 2p sublevel compared to the first electron from that 2s sublevel. So you're going to see an increase there. And then the second electron from the 2s, and then you'll see a much bigger jump when you're going into now the first energy level. So the trends in first ionization energies help us understand not only the existence of energy levels, but also the sublevels in their patterns as well. Okay, so now let's focus in on first ionization energy. The first electron should be removed from an atom. We can compare the first ionization energies of different atoms on the periodic table based on their location, and there's some discontinuities in those trends. So if I'm going to have our periodic table here, okay, and we have our S, D, P blocks. I'm not going to draw the F block. Group 2 and then group 13. That's a 12, group 13. That is going to be the difference between when we have our S and our P, right? So if you have an element in group 2, its outermost valence electron configuration will just be NS2, where N is the principal energy level, the outermost energy level for the atom. If the element is in group 13, the valence electron configuration will be NS2 and P1. All right. So the weird part about this, you would expect the group 13 element to have a larger first ionization energy because it has more protons than the same period for group 2, which would have less protons. So the more protons, you would assume that it has a stronger pull on that valence shell and therefore requires more energy to remove. But there's a slight discontinuity here, and that's because of the existence of these sublevels. It is actually just a little bit easier to remove an electron from the p sublevel than it is from the s sublevel. So the first ionization energy for 13 winds up being just a little bit lower than for group 2 elements when you're comparing them in the same period because of the sublevels. Okay, you're also going to see just a little bit of a discontinuity between groups 15 and 16 on the periodic table. And this one is less about blocks, although I will label them really quick, but 15 and then 16. So group 15 is going to have the valence electron configuration ns2np3, and group 16 is going to have the valence electron configuration ns2np4. And so they're orbital diagrams, and I highly recommend drawing them because it really helps you visualize this phenomenon. The 4 electrons in that p sublevel look like this. So the difference here, you would expect typically in the same period, group 16 elements would have a higher first ionization energy because they have more protons holding on to their valence electrons a little bit more strongly, take more energy. However, you'll see a slight difference in this trend because that last electron for the group 16 elements has to double up an electron in an orbital. So there's greater repulsions between the 2 electrons in that same orbital. So it winds up being a little easier to remove this second electron there compared to the last electron in the group 15 elements. So that, again, is a little bit different than what you would expect based on the trend. So an example question for how this could be asked, explaining the reason for the small decrease in ionization energy between beryllium and boron. You just need to look at what groups they're in. Beryllium is in group 2. So it's going to be 1s2, 2s2 versus boron, which is 1s2, 2s2, 2p1. And so beryllium has 4 protons, boron has 5. You would typically expect boron to have the higher ionization energy because it has more protons. However, there's a slight decrease. Boron's actually just a little bit lower, and that's because the electron that's being removed first is in that p sublevel, which has a slightly higher energy than the 2s sublevel. So the reason there needs to focus on the electron that's being removed, and your explanation when you're phrasing it needs to be, so instead of saying like the 2s, the full 2s is very stable, that's not a very good explanation. It's true, but it's not getting to like the reason why. The better answer is referring to the electrons being removed. So this one being in a p sublevel instead of the s sublevel is a little bit easier to remove, a little bit higher energy, a little bit further away from the nucleus. So it's not being attracted as strongly by those 5 protons compared to beryllium's 4.